Hi folks, and welcome back to Math with Captain Rod. The purpose of this video is to demonstrate how to calculate both area and arc length in polar coordinates. So what we're going to do here is we're going to look at the curve defined by r equals cosine of 3 theta, which I've got kind of a little bit of a sketch of. And, it's not a perfect sketch, but it's good enough for the calculation. What we're going to do here is we're going to calculate the area bound in one of these petals. And then we're going to calculate the arc length around a petal. So we're going to start with the area calculation. Now, anytime you're starting with the area calculation, the first thing you always do is draw your differential element. So in a standard calculus class, or in most problems that are Cartesian types of problems, that would usually be a rectangle or sometimes a trapezoid. Right? In polar coordinates here, our area elements are triangles. So you got to imagine a triangle that looks something like this. And again, you got to imagine it pretty small. When I say small, imagine this angle here being quite a bit smaller than that. This angle here is a d theta. And again, from all my previous videos about integration, how this interacts with the curve here, whether it goes through this point, or the middle, when you're going to use an infinite number of rectangles, which when you're setting up for an integration, that typically doesn't matter. The only time you'd really pay attention to this if we were going to estimate this using like maybe 5 rectangles or 10 rectangles. But, from integration methods, you have what are called upper bound estimates, lower bound estimates, and you have midpoint rule, trapezoid rule. When you use an infinite number of rectangles, those will all converge to the same numerical value. All right, so I'm going to set up integrals for these things. All right, so the area of this triangular element, dA, is equal to 1/2 r squared d theta. So the total area is going to be the integral 1/2 times cosine squared of 3 theta d theta. All right, now let's talk limits now. If we could integrate all the way around, but this problem is symmetrical, so I think what I'm going to do here is just go from 0 to this upper bound on theta, which we'll find in a minute, and then multiply it by 2. So my lower bound is going to be a 0, because this curve starting here, that's the point 1, 0, meaning the distance is 1, the angle is 0. And then we're going to integrate that angle until we get to here, where the radius is 0 again. Now we're going to have to actually calculate that angle. I don't believe that that's actually pi over 2. If you think about how a cosine curve works, if you start at theta equals 0, and then you increase theta, the first time the cosine function is 0 is at pi over 2. However, this is cosine of 3 theta, not theta. So at that point here, we can say that 3 theta is equal to pi over 2. So theta is equal to pi over 6. So what I'm going to do in this integral is run this 0 to pi over 6. That will give me the area of the top half of this curve. And I'm just going to multiply it by 2 to include the bottom area. The problem, these curves are symmetric. So now, let's see. Basically now we're going to have, those 2's will cancel, that's kind of nice. So integral 0 to pi over 6. Okay, integration of powers of sines and cosines. So cosine squared, that's an even power of cosine, so that can be written 1 plus cosine, I'm going to write this down and then look it up and check my memory. 1 plus cosine 6 theta over 2 d theta. I'm doing this from memory here, but I believe there is a trig theorem that says cosine squared of any angle theta is equal to 1 plus cosine of 2 theta over 2. Correct? Yeah. All right. So what I've done is taken that cosine of 3 theta, written it 1 plus cosine 6 theta over 2. Okay. Now, we got 2 integrals going on here. The first one is no problem. The integral of 1/2 d theta, that's theta over 2, evaluated 0 to pi over 6, minus. The second integral is the integral of 1/2 cosine of 6 theta d theta. The antiderivative of cosine 6 theta is sine of 6 theta over 6. And there's also a 2 there, so I'm going to make that a 12. And again, that's going to run 0 to pi over 6. All right, equals. Okay, so this guy right here, if we take pi over 6, and that's divided by 2, that's pi over 12 minus 0. Minus second limit. When we insert pi over 6 here, we're going to get sine of pi, which is 0, minus the sine of 0, which is also 0. So we end up with pi over 12. I'm going to put SU for square units. All right, so important things about the area calculation. Always draw your element. The differential variable here is the d theta. Write down the area of that element. For that triangular element, its area is 1/2 r squared d theta. R will typically be defined by some function of theta in a polar problem. Be careful with your limits here. It might have been an easy mistake to believe this was 0 to pi over 2, but it's not. The cosine function is 0 the first time at pi over 2. However, that isn't cosine theta, that's cosine of 3 theta. So be cautious when you're finding your limits. In this case, 0 to pi over 6 is the correct limits for that area calculation. All right, so now I think what I'll do here is look at a arc length calculation while we're sitting right here looking at it. So first I'm going to do is get rid of this. I don't need this anymore. All right, so now to do an arc length calculation, we're going to need to draw an arc length element. So I'm going to draw, it doesn't matter where in this curve I draw it, I'll just draw it maybe right here. There's a little ds. And if I blow that ds up, it can be expressed in terms of a dr, a change in area, and an r d theta. Oops. Well, my picture could have been a little better. Let me just redraw that a little bit. All right, so you have a ds, a dr, and an r d theta. The Pythagorean theorem relationship for this is ds squared equals r d theta squared plus dr squared. Factoring out a d theta squared and then square rooting everything, we're going to have ds is going to equal the square root of r squared plus dr d theta squared d theta. Now in our problem, r is cosine 3 theta, so this is going to read square root of cosine squared of 3 theta plus dr d theta squared. So here's r, dr d theta would be minus 3 sine of 3 theta. I'm going to go ahead and just write that 9 sine squared of 3 theta d theta. And I'm just going to do the same thing. I'm going to run that integral 0 to pi over 6 and multiply it by 2 to get the bottom half. So this integral should, if I've calculated everything, should calculate the arc length of one of these petals. Now, this integral here looks like a little bit of a pain. What I'm going to do is go to my favorite method for killing off pain in the butt integrals, which is numerical. So what I'm going to do here is minimize this, bring up Microsoft Excel. I'm going to pause the video while I do this. Okay, folks, so I'm back here and I've kind of cleaned my space up here and got rid of what I don't need, and I want to focus here on what I need. So what we're going to do now is talk about how to integrate this expression, 2 times the integral pi over 6 square root cosine of 3 theta plus 9 cosine squared of 3 theta plus 9 times sine of 3 theta squared d theta. Now, what I'm going to do now is think of this right here. This is actually the whole thing, including the 2, is some function of theta. Some things to note. Well, if I put 0 in for theta, this thing is 0, cosine of 0 is 1, so this is equal to 2. This function right here goes through the point 0, 2 when we include the 2. This function is positive definite everywhere in the interval pi over 6. I know this because cosine squared is positive, sine squared is positive. Furthermore, both of these are positive on this interval anyway. So this function here looks, something like this. Now this was just a kind of a sketch to get me going. This does not represent the actual shape of the curve. I don't need the actual shape. I've already taken note that I know this thing's positive everywhere. I also can see there are no asymptotes to worry about in this region. So if I consider this as a function times theta, and I were to graph that function against theta, this integral represents an area now. Basically this area right here. So now what I'm going to do here is talk about how do we find that area numerically. So we break the problem up into little rectangles. Again, because this is now a Cartesian graph. Now, how many rectangles? I'm going to choose n equals 10 rectangles. The width of these rectangles, delta x, I can get from b minus a over n. The upper bound is pi over 6. The lower bound is 0. So pi over 6 minus n is pi over 60. I'll just leave this pi over n here when I set up the calculation. Whoops, I'm sorry. Pi over 6n. If I take pi over 6, divide by n. So this is going to give me the width of these rectangles for any value n that I choose. Okay. Now, you'll notice that if we choose a number, if we choose to break this up in n triangles, we've kind of introduced a variable now, a counting number. So this one is the first rectangle, second rectangle, third rectangle. I'm going to use the letter I here as a dummy variable that represents the rectangle number. So this would be the I equals 1 rectangle, the I equals 2 rectangle, the I equals 3 rectangle, and so forth. All right, now I'm going to go ahead here and start working on things. I got to flip my computer around to do this. All right, so we have a lower bound, which I typically call A, and that's 0. We have an upper bound B, which in this case is pi over 6, and I think I'm just going to do, let's see, equals 3.14159 divided by 6 and see if that'll calculate a value. Yep. All right, we have a number of rectangles here. I'm going to start with 10 and modify if I don't feel like that's accurate enough. And the first thing I'm going to have this calculate is my delta x, which is equal to b minus a. When you set these up, don't forget to close your parentheses. Divide by n. So in this case, my delta x here, actually these are thetas. It doesn't matter if we call it x's or thetas. Let me go back, I guess, and make it match my integral here. I'm just going to put delta theta. Boom. All right, so my delta thetas are 0.05. All right, now I is going to take on these values. 1, 2, 3. Excel's really good once you show it a pattern. There's 10 of them. First thing I'm going to need are my thetas. Now, if I go equals I times my delta theta, grab and drag. Now, you'll notice that there's errors in spots. If I click on one of these errors, you see that red box. That's not where it's supposed to be here. That was supposed to be up here. And this occurred because anything you reference up here has to stay locked down. So I'm going to go back to the original. Oops. my original formula. And the way you lock it down is just hit F4 right behind that value, and it puts these dollar symbols in. I call this double dollaring. Now when we grab and drag, oops, gotta go all the way. There we go. So now we're going 0 to about 0.523 radians. Okay. Now, the way I've set this up is very similar to my picture. This gives me the right-hand side of every one of these rectangles. I will get a better estimate if I use the midpoint rule and set this up to give me the center of the rectangles. So I'm going to go back to the original formula and subtract, let's see, I got to get in here, minus 0.5 times delta x, and again that needs to be, I'm sorry, delta theta, and again that needs to be double dollared. 99 out of every 100 of these I do, x is the variable of integration. Okay, so all that did is adjust them slightly so that now I'm using the midpoints to calculate the function values as opposed to the right hand side of the rectangle. That should give me a little bit better estimate for that integral. Okay, next thing I'm going to need the function values. I'm going to call this capital F. I don't feel like looking for it, so I'm just going to type it, capital F of theta equals. In all this work, this is what's going to take the longest. Now what I got to do is I've got to type in this function. So 2 times parenthesis. Now I'm opening a parenthesis here. At the end of this, what I'll do is square root the whole mess. Let's see here. Actually, I'm going to back up, and I'm going to actually work this slightly different after thinking it through a little bit. I'm actually going to go back and have it calculate cosine. Actually, I'm going to have it calculate 3 theta. And the reason is because then I can reference that here and here, and it'll be a little bit easier when I put this function in. So 3 times theta is equal to 3 times these things. There we go. Now I'll go ahead and do my f of theta, which is equal to, I look over here, I need that 2, so 2 times, there's my times, I'm going to open a parenthesis. Okay, cosine squared of 3 theta. Oops. 2 times cosine 3 theta. Oops, doesn't like that. Cosine, darn it, why doesn't it like that? All right. I think I'm going to do this here, if you just bear with me, folks. I'm going to go ahead and just have it calculate cosine of 3 theta equals cosine of 3 theta. Boom. Okay, then I'm going to go next door and have it calculate sine of 3 theta equals sine of these. Oops, doesn't like that. Sine of 3 theta. We'll get to the function. All right, I'm going to make this a little bigger now. Okay, finally now, our f of theta equals 2 times parenthesis. All right, so now we need cosine 3 theta is this value, and it needs to be squared. I'm a little slow because I'm not working with a full keypad here. Plus sine of 3 theta also needs to be squared. And then multiplied by 9. Now, I'm going to close that parenthesis off. That entire thing needs to be square rooted, so I'm going to just raise that to the 0.5 power. Darn it. Why doesn't it like that? Doesn't seem to like that 9. I'm going to get rid of that. Okay, I think that 9, let's put it right here. 9 times, whoops, 9 times, there we go. Darn it. D squared plus 9 times this squared, black parenthesis. Oops, I got one too many parentheses in there. Actually, I got one too few. There we go. Okay, hopefully that's right. There's our function value. Now, in an area calculation, you have to take that function and multiply by our delta x now, because remember what I've done here is that we're working an area problem now, so I still need to multiply that by the delta x. I'm just going to put a sub I for the area of the ith rectangle is equal to this guy times delta x, which anything you refer to up here has to be double dollared. I believe that was delta x. Oops, I got to go back and get it so I can see what that column is, but got to double dollar that. And finally, I'm just going to do this. This guy is equal to the sum of all of these, 2.27 or 2.28. Now, I'm going to take a moment here and go back to our original problem and just check this for sanity. Remember, look at our graph. From here to here is 1. That makes, just geometrically, from here to here a little bit bigger than 1. Just looking at it, I would have guessed it at about 1.3, and there's 2 of them. So I was going to guess around 2.6. I'm pretty confident that 2.22 is probably spot on. So again, I'm going to talk about the numerical method here just for a little bit more. Again, what we did, or what I've done here, is we wrote our integral for our arc length. However, that integral is a pain in the butt type of integral. You know, I'm not even sure how to attack it. Cosine squared of 3 theta plus 9 times sine squared of 3 theta d theta. Lots of different integral techniques. Numerical methods really only have one hindrance. Can you compute function values? As long as you can use something like Excel to compute these values along the way, numerical methods pretty well always work. So the idea here is to call this some function. And I did a little graph here, and again, it's not important that the curve accurately represent the function for this. The important thing is I know that that function is positive definite everywhere in that interval, and I also took a look at it. There's no asymptotes or anything weird to worry about. Now, this is an area problem. If I graph this function against theta, and I take that function times d theta, that's now an area calculation. Okay? So, and again, you can review my previous videos on how numerical calculations are done. I think I'm going to probably end this guy right here because it's starting to get a little long. Anyway, I hope this video helps demonstrate how to calculate arc length and area in Polar. Have a great day.